if you coordinate ahead of time, right? We have options if you coordinate ahead of time that we don't have if you didn't. And that's all there is to it. Okay. I don't want hot milk. So one of the things I have posted to Canvas this morning is I posted slides for today. The other thing I did this morning is I pushed off the first time homework is due by a week. All right? So you're going to be turning in homework in the lab period. For all of you, I think that's Tuesday night, right? So I pushed that off by a week because I pushed it off for chapter 1 by a week because I did not get chapter 1 slides ready for today, and I don't have that material ready for you to review, right? I am not the only one having hookup. I mean, there have been a lot of hiccups. I've never had a gen ed course. I did not know how many hiccups there were with gen ed courses getting started. Everything else I've taught has been upper level, which you tend to start and go, and day 1 you're going. Gen ed, a little different. And I ended up being one of the hiccups. All right.
You said you posted slides for this stuff?
Yes, I did.
Where did you post it at? Like, what in Canvas?
Okay. So you go through modules in Canvas. This is how I organize things on Canvas. And so you'll see here we have, right now we're at preview the cosmic landscape, right? Just the overall big, broad brush picture of the universe. And you can see here is where we have the quiz, we have the homework, and we have the slides. Okay? And so when I get the slides, finish the slides for chapter 1, they'll show up in the module for chapter 1. So I organize everything by module, by chapter. Everything pertaining to that chapter will be there. You'll see when we start talking about the exam, right? When we start talking about the exam, I have a module for the exam, and I'll put notes about the exam here. Right? So leading up to the exam, there will be things that show up here. We'll talk about them. We'll talk about what the exam is going to cover, and all that stuff we talk about will end up there as a note. Right? And so if you have questions leading up to the exam, what I'll actually post my notes about the exam is a discussion board. So if you have questions about the exam leading up to the exam, ask the questions there, and that way everybody gets the answer right away. Whenever someone sends me any question leading up to exam, I almost always turn it into something for everybody. Because here is my assumption: if you have a question about something, at least a third of the class has the same question, right? That's the sort of bottom end. Usually 2/3, maybe the whole class has a question. So never, if you're sitting in here in this class and you're confused about something, never assume it's just you, because I guarantee you it is not, right? It is not just you. Yep.
When you say you're turning in the assignment on the lab here, you mean turning it in Canvas or actually turning it in?
Turning it in. Handing it in. Right? So at the lab period, we're going to physically collect the homework. The quizzes you do online, right? But the homework you'll do by handing in. Other questions?
So like for all of the assignments that we have right now, like your office hours and all that, that's through Canvas?
That's through Canvas.
And that's all due tomorrow, right?
Yes. The only one that's not through Canvas, because it's impossible to do through Canvas, is come find my office.
And we just have to like write our name and then submit it, and that's it on the
Yeah.
Canvas stuff?
On these, yeah, you just write your name and submit it. Right? On this one, there are sheets up on my door. It doesn't matter what section you're in, it just says Astronomy. Sign one of the sheets that says Astronomy. Right? Why do I want you to find my office? want you to know where my office is. So you can find me when you have to, right? Because when you have to find me, you're going to be stressed. You've been to my office once, and you can find it without any problem. That's a good thing, right? Now, this is an assignment I started last year, back when I had classes last year in 3 different buildings on campus, none of them in which my office was in, right? This year, this is the only class I have outside of my building. In fact, all the rest of them are just down the hall, but I still make those students do it so they know where the office is, right? Because eventually you're going to have something come up, you're going to want to see me, you're going to want to know where I am. The 2 pieces of information you really need to know are when I should be there and where I am, right? So keep those 2 pieces in mind. All right, now, some of you go by a name other than what's in Canvas. I may eventually remember that. I'm going to call out your names, tell me that you're here. If you go by a different name, tell me that it's different. When I call out your name, make sure you do something and then I look at you, because I'm trying to get to know who you are. Okay? So, Eureka. Okay? Michaela.
Here, I go by Bryn.
Bertrand, yes. The more I see it in print, the closer I'll get. Laurel. Carly. Kelly. Joe. Dakota. Anna. Carrie. Samantha. Robert. Diamond. Marjwan. Dylan. Tanisha. Maisie. Anna. Justin. Emily. Caitlin. Chelsea. Bailey. Bernisha. Shelby. Colton. Tony. Colin. All right, so last time there's a snafu on this website about when the lecture is for section 2, so almost nobody was here for section 2. See if we're doing better this time. Stacy. No Stacy. Chandretta. Stormy. Samantha. Scott. Rolanda. Sheldon. Marquavius. Maria. Reginald. James. Keyshawn. And Sydney. Okay. So today, we're talking about a little thing we call the universe. All right? So we start. Let me get this downloaded real quick. We start with our review of the universe someplace close to home, which is coming up shortly. Okay, so this is us. Well, actually, that's Africa. Madagascar. You always want Madagascar when you're playing Risk. So this is us. This is the Earth. We have a radius. That means the distance from the center of the Earth to the Earth's surface. That's an average because the Earth's surface isn't flat. If you've not been out of the Delta, you may not know that, but the Earth's surface isn't flat, right? So we have a radius of 6,371,000 meters. Meters about that long, right? 100 meters is a football field plus 10%, right? We've got about 7 billion people, and we are 149 billion meters from the sun, give or take. I say give or take because we don't actually go in a circle around the sun, right? We go in an ellipse. An ellipse, when you think you want to, everybody know what an ellipse is? Anybody not know what an ellipse is? Okay, so an ellipse is like a circle, except you stretch it out a little bit in one direction, all right? So if an egg were symmetric, it would be an ellipse, but it's not, it's lopsided. So an ellipse is like a circle that's stretched a little bit in one direction. The ellipse that we go in is very close to a circle. So close that we don't worry about that difference very often. Right? It makes a little difference, but not a lot. So on average, we're about 149 billion meters from the sun. It takes light from the sun about 8 minutes to get here. Right? 8 minutes. The moon. How many of you think the moon is really far away? How far away do you think? Well, it's up there. So, population 0. But, how far away is the moon in terms of human terms? All right, I'll give it to you in something similar. I have meters here because we're going to use standard international units here. Right? There are only 3 countries in the world that do not use standard international units. They are Burma, Liberia, and the United States. All right? And while you may not realize it, we are slowly but surely converting to standard international units in the U.S. The last few things to go will be miles, miles per hour, gallons. But if you're in medicine, or if you're ever taking medicine, you now take milligrams, milliliters, right? We use, and cars, if you're my age, we used to talk about cars, oh, that's a big engine. It's a 485. That meant 485 cubic inches in the cylinder. Well, now we don't say it's a 485, we say it's a 6-liter engine. We've converted to metric on when we talk about cars, right? It's kind of funny when you see the Ford Mustang with 5 liters on the side, right? Yeah, that wouldn't have happened when I was a kid. All right, so the moon, 384 million meters away, right? About 250,000 miles. I have a car that's gone 269,000 miles. So I haven't made it back from the moon yet with that car, right? But I made it to the moon. It's pretty close, right? It's pretty close. To go all the way around the Earth, if you were to hop on a plane and fly all the way around the world like they just did with this solar-powered plane, you would travel about 24,000 miles, right? Which is about how many kilometers?
I got it.
You got it? Okay. 38,000 kilometers. All right? So, and look at the moon. Radius of the Earth, all right, 6 million meters, or 6,000 kilometers. Radius of the moon, 1.7. All right? 1,737,400 meters. The moon is smaller by a good bit. Now, some have argued we might be considered a double planet because we have two fairly large celestial bodies here together. And in fact, the moon is big enough that the Earth doesn't rotate, doesn't orbit, or the moon doesn't orbit just around the Earth. The Earth and the moon orbit about their common center of mass, but that center of mass is inside the Earth. It's not at the center of the Earth, but it's inside the Earth. Of course, currently the population of the moon is 0. It's never risen very high, and only for brief periods of time, right? All right, so that's the Earth, and that's the moon. I'll eventually bring in, when we get into going over the planets again, what would the sky look like if all of these planets were stuck where the moon is? Right? It's a pretty cool visual to see. So in order from the sun outward, we have Mercury, Venus, Earth, Mars, Ceres, which is not really a planet. Ceres is a dwarf planet. It's been in the news lately. It's probably been in your Facebook feed if you do any science stuff at all on Facebook. Ceres is a good-sized dwarf planet in the asteroid belt. And we currently have a probe in orbit around Ceres taking pictures of it. All right? Then Jupiter. Jupiter's the big one. Jupiter is larger than all the other planets combined. Right? It's not really drawn to scale here. But you could take all the other planets, put them together, and they'd still be smaller than Jupiter. Jupiter is the first of the gas giants. So these, Mercury, Mars, Earth, Mercury, Venus, Earth, Mars, they are all rocky planets. By rocky, I mean, right? They're solid. Jupiter is not. When you look at Jupiter, you're seeing the surface of the clouds. And Jupiter is almost all cloud. It's all gas, right? Down in the middle, there's a bit of something, but you can't get there. Jupiter is also, because it is so large, it's not, depends on exactly the stellar mechanics, we'll get to at some point. Jupiter is somewhere between 50 and 500 times too small to become its own star, right? But even as it is, Jupiter puts off more radiation than it gets from the sun, right? All the other planets, well, Saturn also puts off more radiation than it gets from the sun. Everybody else absorbs more from the sun than they put out. So gravity is driving a mechanism in Jupiter where it emits thermal radiation. All right, so after Jupiter, there's Saturn, right? And if we ignore Ceres, if we take these planets up through Saturn, for the longest time, that's all we knew about. And that's all we knew about because we did not have the instruments that would let us see these other planets. They are so far away. Even though Uranus and Neptune are large, they're so far away we couldn't see them until relatively modern times. Okay? So these, all of these, with the exception of Ceres, you can see in the night sky Mercury, Venus, Mars, Jupiter, and Saturn. You can see them with your naked eye. All right? Uranus, I forget when we discovered Uranus, we'll get there. Uranus and close observations of Uranus led to the discovery of Neptune. Because what would happen is Uranus and Neptune are going around in a circle. Uranus is going around faster, right? Because it's closer to the sun, it's going around faster. And as it got close to where Neptune was ahead of it, it would speed up. And then as it passed Neptune, it would slow down because of the influence of Neptune. And so as we watched Uranus carefully, we figured out, oh, there's got to be something else out there that's making Uranus speed up and slow down. And so we started looking for it, and we found Neptune. Then, less than 100 years ago, right? Less than 100 years ago, we found Pluto. Pluto, for me, for people my age, big controversy over whether it's a planet or not. We now call it a dwarf planet. But it's been less than 100 years since we found it. And we tend to think of planets as things that have been around for a long time. We've known about them for a long time, right? But Pluto's still relatively new, and that was the first, it was the first big discovery by an amateur astronomer, right? Someone just playing around in their backyard found Pluto. Well, playing around in the desert, but someone just playing around in their backyard found Pluto. So, one of the reasons Pluto started off life as a planet, Pluto's kind of weird in a lot of different ways, but the biggest reason it started off life as a planet is when we first estimated how big it was, we thought it was roughly the size of the Earth. Turns out it's not, it's a lot smaller, right? It's a lot smaller. And then out past Pluto is Eris, which is way out there. And these distances for these planets are a little hard to wrap our brains around sometimes. But here we have two things. One is the radius of each planet, right? So Pluto and Ceres and Eris are not on this list because they're not planets, they're dwarf planets. All right, so here's the radius of each planet. You can see Venus and Earth are pretty close to each other. Mars, about half the size, half the diameter. Mercury, smaller still. But then you get up to Jupiter. Jupiter's over 10 times the radius of the Earth. Right? Now, when you think about that in terms of what that means in terms of the amount of material, right? A ball this big versus one with a radius twice as much, right? Well, the one with twice the radius has a lot more material in it than one with half the radius. Because every layer you add adds a whole bunch. That's why a medium pizza is 14 inches and a large pizza is 16 inches, because you add those 2 inches and you've actually added a lot of pizza. Right? So, Jupiter, large. Saturn, large. Uranus and Neptune, 4 times as large as the Earth. And this picture gives us in with the sizes drawn proportional to each other. So if this is the Earth, right? Jupiter looks that big. Right? Saturn, Uranus, Neptune. And then you can see this little speck here, that's Ceres. Right? It's hard to see. It's just a little dot, the dark spot there. That's Ceres. And then out here, Pluto and Eris, they're tiny. Right? They show up as little dots. The moon, I wish it actually had the moon in here, because the moon is comparable to Pluto in size. Right? The other weird thing about Pluto is its orbit, that we will eventually get to all the planets and cover them and everything. But here, now, the sun, right? This is Jupiter drawn to scale with the sun. This is the Earth drawn to scale with the sun. The sun is over 100 times larger in radius than the Earth. All right? Over 10 times wider than Jupiter. That means it has 1,000 times more material in it than the rest of the solar system. All right? 1,000 times more material. You take the whole rest of the solar system, add it all up. You gotta remember, we started with, you add up all the planets, you don't even get to Jupiter, right? You lump them together with Jupiter, and you're still looking at the sun is 1,000 times more massive than everything else put together that's in our solar system. Right? At the end of the day, the engine that drives the sun is gravity. Gravity is what causes the sun to have nuclear fusion. And the nuclear fusion results in the heat and light that warm us, right? Nuclear fusion is what's causing this to look like it does, which causes all these gases to go out. These are actually following magnetic field lines as they charged gases follow magnetic field lines as they go out. You make these big loops. And, you know, people get scared on occasion because this, you can see the Earth easily fits inside one of these. And occasionally the sun spits out a whole bunch of stuff. Right? Now, fortunately, you know, we occupy a itty bitty tiny piece of the sky with respect to the sun. So the odds of it hitting us are low, but occasionally you'll hear warnings about, you know, we got a solar storm coming, and that may be problematic for cell phones and satellites and things like that, right? That's when the sun has shot one of these things out, all these charged particles going out, and they happen to escape the sun completely, and they're headed our way. Okay? This happens at a low level all the time. How many of you have ever heard of the aurora borealis? Right? How many have ever had the chance to actually see it? I haven't either. All right, just pictures. The aurora borealis is caused by charged particles coming from the sun, getting caught in the Earth's magnetic field. Our magnetic field causes those particles to head towards the poles and hit our atmosphere near the poles and generate that nice, beautiful light show that we have as aurora borealis. Okay. I will eventually bring in, some people do some recordings of what the aurora borealis sounds like, and I'll bring that in at some point. And we'll listen to the aurora borealis. Pretty cool. All right, now we start getting the perspective for what all these numbers mean. And one of the things we like to do in astronomy is we change units so that we can have an intuitive feel for what the numbers mean. Most people, you know, one of the problems we have in talking about things like the national debt is a trillion is a big number. It's really hard for us to think about a trillion, right? So what we do in astronomy when we talk about the solar system is we use a different unit, which we call 1 AU, or 1 astronomical unit. This helps us make the distances between all these objects a little bit more tangible, right? So an astronomical unit, there's no magic to it. We took the distance from the Earth to the sun and said we're going to call that 1 AU. Right? That's no different than how measurements have been come up with for a long, long time. We're just trying to set a new standard, right? How many of you think of, have heard over and over again, Napoleon was short? All right? Napoleon was short. How tall do you think Napoleon was in his shortness?
14.
No.
5'4".
Napoleon was actually my height, which was average height for his time. The issue was the French king's foot was longer than the British king's foot, and so feet in France were longer than feet in Britain, and so in French measurements he was 5.5 feet 2 inches, and in British measurements he was 5 feet 6 inches. And the Brits took the French number and said, we've got a propaganda thing we can say. He's short. Right? It's because this measurement of a foot depended on how big the king's foot was. Kind of arbitrary, kind of stupid, you know. And you get a new king and suddenly your house is bigger? No, your house is the same size, right? Your house did not change size. the distance from one town to another did not change, right? So it took us a while to begin to develop this notion that we need some sort of standard for units. The meter is still an arbitrary standard, but it's one we've all agreed upon. All right, we know what a meter is. I kind of like a meter because that makes a centimeter about the size of my finger, right? The width of my finger is about a centimeter, right? So that's easier than trying to guess how big an inch is all the time. Centimeter. Right? No, yeah, not that. Oh, the width. Right? So we define the distance between the sun, here's the sun, and in this picture, the earth is this ring right here. Right? It's clearer in the book. So the earth is here, the sun's here, that's 1 AU, that distance. Okay? And that makes Mercury at 0.4 AU. But then Neptune, we have to go over to this picture, Neptune is all the way out here at 30 AU. Right? And this picture, what this picture means is, here is the circle. It's an ellipse, but it's very close to a circle, so we'll say circle all the time. Here's a circle Mercury makes around the sun, Venus, the Earth, Mars, right? So all of this shrinks down to here, right? And then we get to see the rest of the planets, Jupiter, Saturn, Uranus, and Neptune. Right? Now, here is the asteroid belt. The asteroid belt is a collection of rocks. Right? You know how Saturn has a ring? The asteroid belt is kind of like a ring around the sun. It's just a collection of rocks. But it's rock, while Saturn's rings are mostly ice. So Saturn's rings are bright, have nice colors. The asteroid belt's hard to see because rock tends to be dark. Right? And dark rock doesn't reflect sunlight, it's hard to see. Well, this asteroid belt, if Jupiter had been a little further out, this asteroid belt probably would have become another planet. Right? And Ceres represents, in some ways, the attempt to form another planet there, but because of Jupiter and the gravitational disturbances Jupiter has for that area, it's impossible to collect enough rock together in one spot to form a planet. Right? Normally what happens is rocks through gravity slowly come together. And once two rocks come together, they have more gravitational attraction for a third rock, right? And slowly over time they all collect and you end up with a planet. There would be a planet that would gradually collect off all the rocks in this ring, except that Jupiter keeps that from happening. Right? So here we have Jupiter's pretty close, Saturn's pretty close, and now you begin to get a good idea. Remember, Jupiter's big, Saturn's even bigger when you take into account the rings. Then Neptune and Uranus, or Uranus and Neptune are a little smaller, right? And they're a lot farther out, which is why it took us so long to find them. Right? They're farther out. Because they're farther out, they get less sunlight. Because they get less sunlight, they reflect less sunlight. Neptune in particular is kind of dark. Right? Uranus is kind of bright, Neptune's kind of dark. So Uranus was easier to find than Neptune because of that. And Neptune is much farther out. Now comets, we have a comet, there's a comet that's going around the sun right now that has a probe on it called PHY, and a probe circling it called Rosetta. Right? We managed to land a probe on a comet, and right now it's going around the sun, still collecting some information about comets that we've never been able to collect before. Among other things, we've discovered this comet has many more organic compounds on it than we expect. So if you're a chemist, and you know what an organic compound is, that turns out to be a little surprising because we think of organic compounds as hard to make, but here they are on this comet. Right? All right. Comets go way out. This is why people argue about whether or not Voyager 1 is outside the solar system or not. In some ways it is, in other ways it isn't, because comets going around the sun go all the way out to 100,000 astronomical units. And Voyager 1 is only 40 AU away right now. Right? All right. Now we pan out a little bit. This is the world's largest selfie. This is a photo taken by Voyager 1 of our solar system. That's the sun, right? That's Venus. That's the Earth. Mercury was too close to see. Mars was behind the sun and too close to see. There's Jupiter. There's Saturn. There's Uranus. And there's Neptune. Okay. Voyager 1 is far enough out to take a picture of the solar system. It'd be pretty cool, except that it's a one-way trip. And here you can see what all those, what all the orbits of the planets look like. There's a good picture I'll find again and share here sometime that the Mars rover took of the Earth from on Mars. And you get to see the Earth from Mars. It's just a little star in the sky, a bright star. If you zoom in close, you can see the moon next to it. All right. Now, because we live in the delta, you can almost imagine seeing the Milky Way. One of the things you have to remember is we have a lot more light than people did even 100 years ago. And you back up 200 years ago, there's almost no light outside at night. And so people saw the stars a lot better for several reasons. One, pollution. Two, light pollution. Right? Astronomers call it light pollution. We have light getting in the way of us seeing the stars. So if we went way out in the middle of nowhere in the southwest, up in the mountains, we could see the Milky Way.
I've seen it. Pretty awesome.
It is pretty awesome, right? It's pretty awesome. I've seen it. I've even seen it here in the Delta, but that was in the mid-'80s, right? I would go home. My parents were in Vicksburg. I was going to school at Ole Miss. I'd go through the Delta on my way home, and I'd stop. I always headed home really late, so it'd be like midnight. I'd stop in the middle of nowhere in the Delta with no lights on for miles, and I'd look up at the sky. Right? Because if it gets really, really dark, you can see the Milky Way. What is the Milky Way? Well, we are in our galaxy, which we call the Milky Way. The Milky Way is an old term. The Milky Way goes back from before we knew about galaxies, before we knew about planets, really. The Milky Way is a description of what our galaxy looks like in the sky. Because it is a concentration of stars that go across the sky. Right? And that concentration of stars looks milky. Right? It became the Milky Way. This is a photo using astronomical instruments looking towards the center of our galaxy. Right? So when we look with our naked eye, we don't see this, but we do see there are more stars, right? Across this band, across the sky. And it's really startling because most of the time we never get to see it. Mostly because of light pollution. But, I mean, you think 200 years ago, 1,000 years ago, you had nothing else to do at night. You look up at the stars. Right? People thought about what is all of this. This is a reconstruction of what we believe our galaxy looks like. We are in a spiral galaxy, and you can see why it's called a spiral galaxy. Right? And we can tell it's a spiral galaxy because we make observations heading this direction, and we can see where there are areas without much stuff, and then more stuff and not, and then more and not, right? We can kind of see that structure with different astronomical instruments. We do searches along different wavelengths. We get to map that out.
That's a big thing in the book.
Okay. In the middle, the galaxy gets dense enough that you really can't map out an individual structure. It's more like just a big blob, and it also bulges. You can see here it bulges up and down. At the very center of our galaxy, we believe there is a massive black hole. And in part, we believe that because when we look at other spiral galaxies, we find at the middle of them a massive black hole. And one of the things that took us a long time to learn in astronomy is we're not special. All right? It took a long time for us to learn we're not special. We went for a long time with, our star, our sun, the star, all right? Our star, the sun. Our star, the sun, must be the only one with planets. It's got to be a rare thing. So now we've found, almost 2,000 planets around other stars. And I was in Europe, it was 92, when they first found the first planet around another star. All right? 92, University of Geneva. They found the first planet around another star, and everybody's like, wow, this has got to be a really rare thing. And I'm thinking, no. We already have examples. If it exists, it probably exists a lot. And this is one of the things we've been up against in astronomy is, it took us a while to get to, now we look out and we see other spiral galaxies have black holes in the middle. We probably do too. Right? And a black hole, we'll talk about later in the semester in more detail, but a black hole is simply you've gotten enough matter together, right, that not even light escapes. Okay? So that's why I call it a black hole. Black hole is a hole simply because, nothing ever comes out of it. It goes in, it stays, even light. If you're a fan of Stephen Hawking, we can talk about, quantum evaporation of black holes, but that's a technical detail we don't really need to worry about. If it goes in, it stays. Right? How big is our galaxy? All right? The radius of our galaxy is 50,000 light years. Now we've introduced another unit, a light year. The reason we introduced another unit is because trying to describe the size of our galaxies in meters would be nonsense. Trying to describe it in terms of AUs would be nonsense. The numbers are too big. Even at light years, the numbers get to be really big, right? But our galaxy has a radius of 50,000 light years, 100,000 light years wide. What is a light year? Light year is, we'll back up to these, right? Talking about distance in terms of years might sound like nonsense, right? I mean, distance is a distance. It's meters, miles, kilometers. But we talk about Memphis being two hours away, right? Jackson's 2 hours away. Oxford's an hour and 45 minutes away. We talk about distance in terms of time all the time. And we do that because there's a speed limit on our roads. We're not going to go an arbitrary speed going to Memphis. And so how long it takes us to get to Memphis, or anywhere for that matter, is sort of a predictable thing. And so we tend to talk about how far away things are in terms of how long it takes to get there. Okay? We all do it, and we don't think about it. A light year is nothing more than how far light goes in a year. Now, light goes a long way in a year, and this is why we don't do it in meters, right? This is, what's this? Millions, billions, trillions. What's after trillion? You might remember what's after trillion? Quadrillion? Right. 9 quadrillion, 454 trillion, 254 billion, 955 million, 488,000 meters. Right? You know, light travels 3.3 million football fields a second, so it's fast, right? So when we talk about 50,000 light years, we're talking about it would take light traveling this fast 50,000 years to go that far. So it takes light 8 minutes to reach us from the sun. It takes light 8 hours to reach Pluto, right? And it takes like 18 hours from the sun to reach Voyager to charge its solar panels. It doesn't get a lot of light anymore, right? It's really running on what little fuel it has left. So that's what we mean by a light year. And the reason we use that for interstellar distances is because meters and AUs know